All right, so homework 4 is all about limits. And you kind of, even though this typically is not what happens, you get in the habit of to evaluate directly things that trick you. So maybe let's just start with some examples. And then maybe we can talk about conceptually what a limit is. Okay. So we have a function, and when we talk about limits, we're interested in how the function behaves as x is approaching a certain point. So, and that the statement that we use when talking about the behavior of the function is the limit. So we want to know the limit of this function as x is close to 5. And we should emphasize that x is not actually at 5. We're only interested in the behavior of the function as x when x is close to 5, arbitrarily close. So you get in the habit of evaluating directly, meaning you just let x, you expect that x is close to 5. You can kind of, by plugging in, x equals to 5. You can probably, if you get a number, 31 over 21, that's perfectly valid, right? So as x gets close to 5, your function gets close to the number 31 over 21, right? So it doesn't have to be nice, but so you kind of get in the habit of evaluating directly. So sometimes you'll get something like x is approaching 5, and we're interested in so if you try to evaluate directly, what would you get? So as x is close to 5, what do you expect x plus 7 to be close to? You just let x become 5. And what about the numerator? 0. Yeah. So you get 0 over 12. And what is 0 over 12 equal to? It does exist. So 0 over a non-zero number, so I'm just going to use 1 as a prototype. The important part is that it's not 0. Is 0. So 0 divided by 1 is 0. 0 divided by 2 is 0. And is that a valid limit? Is that 0 a valid number? Absolutely. Right? 0 is like on the number line. So this is valid. So if you get 0 over non-zero, you're fine. Just know that that's 0. Okay. What we're going to look at for the next example is the kind of flippity-flop of that, right? If you get 1 over, or non-zero over 0, then this is not defined in math. So dividing by 0 is not allowed. 0 in the numerator is fine, 0 in the denominator is not. So if you get like non-zero number divided by 0, I think you're gonna talk about infinite limits, but right now I think in the homework the limit does not exist. So if you just took the reciprocal of the top, right, and you try to evaluate directly, you would get that the numerator is not 0, but the denominator is. And so you'd say that the limit does not exist because you can't plug this. So in the homework, question 1 has these kind of 3 basic examples where one limit, you just get a non-zero number, just line as the limit. The next part, you get 0 as the limit, and that's valid. 0 or non-zero is 0, that's valid. And then the third part of problem number one, you get something like, or one of them, you get like non-zero number divided by zero, which is not allowed in that, zero, so the same sense. So this is like we try to evaluate correctly and recognize whether you get a valid limit or if you're divided by zero and non-zero. So I guess, are there any questions about that?
So the same rule, what would happen if it's like 0 over 0? Isn't that the same thing?
So that's an excellent question, because that's exactly what we talk about next. Right? We tried evaluating limits directly. But then if you get some stuff like 0 divided by 0 or infinity divided by infinity, as we'll see, we get something called it's called an indeterminate form. So 0 over 0 is like we don't know what's going on, and we have to use other algebra tools to figure it out what is going on. So indeterminate forms, let's get some examples. Are things when you evaluate the limit, when you attempt to evaluate the limit directly, I should say. Okay. Right, so try to evaluate that limit directly by letting x go through. And what do you get on top? What do you get on bottom? So you do have that 0 over 0 situation that you are referring to, and this is called an indeterminate form, meaning the limit might exist, it might not, and so we don't know yet. We have to somehow determine, we have to resolve this situation. Okay. So when we look at limits at infinity, I might as well mention it now, we will get another indeterminate form, which is infinity divided by infinity. This also doesn't make sense in that way. Because all that's saying is that you have some function where the numerator gets large and the denominator gets large, but we don't know like which one gets large faster. So if the denominator gets large faster than the numerator, then maybe the limit is 0. But if the numerator grows way faster than the denominator, maybe the limit is infinity. And if there's a balance, maybe you get a finite number of ones. So we'll look at that and we'll look at these other things. But just right now on the homework, all I see are these two indeterminate forms.
So there are different types of indeterminate forms?
Oh yeah. You might get into infinity minus infinity. I don't think so. You probably will get to 1 to the power of infinity when you start talking about logs, implicit differentiation perhaps. Also, 0 times infinity is an indeterminate form. So maybe, I don't know how the scope of your class, but yeah, there are other indeterminate forms. But right now, these are the 2 relevant ones that are logs. So in this example number 4, we have 0 over 0. So that's an indeterminate form. And so how do we determine whether the limit exists or not? Yeah, so if you have polynomials especially, like in your classes, you're going to have to factor, and hopefully we'll have a cancellation after you factor, right? You might not, but. So yes, so we're going to factor. Okay, and some things you'll see are a difference of 2 squares for sure. Or difference of squares, and And so do you remember, like, if you have a number squared minus a number squared, that's called the difference of two numbers squared. And anybody remember what that factors into?
For like x plus x minus 1?
Yeah. Yeah, so it's a, and what do we call these, this pair, the expressions where you have a minus b, a plus b in general? What do you call those? I think they're usually called conjugates. And we'll run into them again when dealing with square roots. Okay. So a difference of two squares factors into conjugates. So we notice that the denominator, in example 4, is x squared minus 9. But of course, we recognize 9 as 3 squared. So that is a difference of two squares. So that will factor into x minus 3 times x plus 3. So we factor the denominator. And by the way, how did we know that x minus 3 actually had, so this is like a tip. If you have a polynomial, right, that's like x squared minus 9, and you evaluate it at 3, and you get 0. You know that one of the factors has to be x minus 3. So that's like the relationship between the roots or zeros of the polynomial and factors. Okay. So in the numerator, we have another polynomial. And if you evaluate it at 3, we found that you get 0, right? So what must one of the factors be? So if 3 is a root of your polynomial, one of the factors must be
X minus 3 is plus 3.
yeah, x minus 3, right? Because if the polynomial when x is 3 gives you 0, then one of the factors has to be something like x minus 3 is 3 minus 3 squared. So that's a hint, right? You don't always, you kind of, if you get 0, for a polynomial, you already know one of the roots or the factors. So we know one of the factors has to be x minus 3. But what would the second factor be in the numerator? So plus, right? So recall that we're looking for two numbers that multiply to give you the constant term. So be careful, that's a negative 6. Right? But that add to give you the coefficient for the middle term, negative 1. And so we see that 3 plus a negative 3 plus 2 works, right? The negative 3 plus 2 gives you the negative 1 for the coefficient of the middle term, the x term. But when you multiply them, you indeed get negative 6. So we know the two factors are x minus 2 and x plus 2. And so now we see that x minus 3 divided by exactly the same thing, x minus 3 is 1, right? And so after we get that cancellation, in a sense, we got rid of that pesky thing that made the top and the bottom 0. And now we can try to reevaluate. Right, so let x go to 3, and the numerator becomes 5, and the denominator becomes 6. And that's a legit number. It's a finite number. So the limit is 5/6. So yes, you get 0 over 0 in the limit problem, and you see polynomials especially. Try factoring, and don't forget about that. Be on the lookout for differences of squares. You know how that kind of stuff.
Good question.
Yeah.
On the first part, 0 as well equals 0. That would be an answer, right? Before that ended.
Which what would be
The one previously where we were like.
example 3?
Yeah. Where it was like. Yeah, I think that one. Where it was like not defined.
Does not
Would that be
exist.
a valid answer? Like 0 to
Well, if you read the instructions, right, it says find the following limits and write D and E, so it does not exist if the limit doesn't exist, right? there is no limit. So when we say D and E, we mean does not exist, meaning the limit doesn't exist. So a number, this is not a valid answer because this is not defined. This is the answer they're looking for. You want to specify that the limit in fact is not exists. You don't get some illegit number. You get I don't know if that answers your question.
All right, that was it. I don't want to put that and then I'm like, solve for this.
Okay, so no, they don't have anything too funky here, so. Okay, so let's try this one. Wait a minute. Actually, let's not try that. It's not a bad problem, but I'm just gonna. I didn't prepare, by the way. It was kind of like the guys.
Oh, that's good.
So 5, -1, so -5. There you go. That'll work. So show your grader that you know that you want to evaluate. Try evaluating the limit directly first. You can tell me what you have as soon as you know what you get here. Just go ahead and roll it out.
I have like, so in situations like this,
Yeah.
is it just better to always think like, what can I factor first? You know, instead of thinking like, okay, first should be the same, right?
No, put it in as the first thing you gotta do.
Oh.
Because they might have a problem where you try to plug in the x value and you get a legitimate number, and that's the limit. So it's like a trick thing, but typically it's going to be you get in some forms, they want to see that you know how to do the algebra to actually determine the limits.
Okay. Thank you.
So what did you get? You tried evaluating directly.
I don't know what exist.
But you already got the answer at the end. Okay.
Oh, sorry.
Let's see. I don't know. I thought I designed it for the limit to exist. So let's see. So if you evaluate directly, right, you get -1 cubed minus the -1 because x is close to -1, and then you get -1 squared minus 4 times -1 minus 5. So what's -1 cubed? Right. Yeah. And what's the negative of a -1? Double negative, not positive. And then -1 squared, and then +4 minus 5. So we see that the numerator is indeed 0, the denominator is 0. So that's an indeterminate form.
I also got 0 and 0, but I keep thinking that 0 and 0 means does not exist.
No, that it's exactly indeterminate, and meaning we don't know. It might not. So, all right, so that's when we see that 0 over 0 or later infinity over infinity, that's when we say, well, we're expected to know some algebra tricks here, right? So since we're dealing with polynomials, probably factoring. So how can we factor the numerator? What can we do first?
See how it is?
Yeah, so we see that the two terms in the numerator, they both have a factor of x. So we just factor that out. And what's left behind in the parentheses after we take out a factor of x?
X squared minus 1.
That's right. And you can see that's correct, right, if you distribute that in the original number. Okay, and what about the denominator? Well, let's actually, is the numerator completely factored?
No.
Okay. Because?
We have to make, I really want to say, we have to make the x into a negative, right? Because it's cubed.
Well, I mean, I know that x going is approaching -1, but that's not relevant to the way you factor that numerator, right?
Oh,
So-
so the, oh, sorry.
Yeah, go ahead.
The x plus 1, x minus 1.
Yeah, x squared minus 1 means 1 is 1 squared. Right, so we do notice that that's a difference of squares, so that factors into the product of conjugates there. Okay. And so what about the denominator?
That's x minus 5 is plus 1.
Yeah. Okay. So now, do we have a cancellation? Okay. X plus 1 divided by x plus 1 is exactly 1. So now we can attempt to reevaluate the limit by letting x go to -1. Well, I guess I thought I was going to get it. So the limit is
So, negative 2 to 6.
yes, or also known as -1/3. All right. Just one. What's 7 times 6? 14. That large enough box?
I agree.
I'm keeping you waiting now. What did you get when you tried to evaluate correctly?
Can we put it on correctly?
Yeah.
Oh, I'm like on like the adding part.
Yeah, of course.
I wish we could just see that part,
Well, I mean, yeah, I know.
I
I
get why we
mean,
did it.
that's an indeterminate form. It's, the thing is you're communicating to your grader that you attempted to evaluate correctly, and you only did algebra because that an indeterminate form. But if you're doing it for yourself, your own amusement on Saturday morning and whatnot,
Good question. So we got one more quiz, that being this one. And we got 2 weeks more material, or next week material, and an example. Will there be anything for the people that's in the exam?
I mean, somebody will be here. So, yeah, I mean, if it's an exam week, then maybe there's no new material, maybe you can just go over what kind of like a review for the exam type of thing.
Yeah, I think the exam is supposed to be.
All right. So did anybody factor the numerator? 2 numbers that multiply to negative 42, but add to give you the negative 1.
I say negative 7 has a 6.
That works. And anybody factor the denominator?
Or I guess it would be -7 times -7.
Yeah. So x minus 7 divided by times x minus 7. Okay, so we do have a cancellation. X minus 7 divided by x minus 7 is 1. So when you try to evaluate directly, what do we get? Oh, no, 13 over 0. You scared me.
My bad.
So 13 over 0. So what does that say in terms of our answer? That's right. So dividing by 0, a non-zero of 15 divided by 0, we know that the limit does not exist. And I'm surprised that you're not talking about infinite limits yet, like plus or minus infinity. So that all the homework was asked was does not exist, right? All right, so it does not exist. So no limit. All right. So again, 0 over 0 indeterminate, polynomial stripe factoring 0 cancels. So next we want to talk about square roots in your problem. And this has to do with conjugates, actually. So if you have, what happens if you have square root of A minus square root of B? So it's like a general formula, and then square root of A plus square root of B, and you multiply those. What would you get? Yeah, right? This is a product of conjugates. So you're going to get the first term squared minus the second term squared, a difference of 2 squares. But squaring a square root gets rid of the square root. So you just get A minus B. Okay. So that suggests that if you have square roots in a limit problem where you have an indeterminate form, you might want to think about multiplying by conjugate associated. So let's do an example like that. Let's make one up. Let's say wait a minute. Okay. let's make it a little bit more manageable. There you go. All right. Of course, I didn't get that right. That should be -4, not 16, so I apologize. Hold on. -2. There you go. Okay, so when you try evaluating correctly, do you get 0 over 0?
Yes.
Yeah. All right, so that's an indeterminate. And so we don't have like a polynomial exactly, right? So, but instead we have square root there. So the thing that you want to think about is just simply looking at the thing that has the square root. So we're looking at the numerator there. And what would the conjugate of that be? That expression.
X whole square root x plus 2 times 2.
Okay. So x plus 2 what?
Minus 2.
All right. So actually not. What's going to happen is, let's see. So that's kind of the tricky part. You have to kind of know how to chunk it correctly, right? So you have two terms here. You have term number 1 minus term number 2. So like a minus b, a would be the square root of x minus b, and b would be the 2. So the conjugate would be square root of a plus b, right? So you don't touch the thing underneath the square root, but rather just change the sign between the two terms in the numerator. I hope, I don't know if that clarified anything.
Is that like a just rule that we're not changing the sign in the square root? It's just anything like if it's not in it, change the sign.
Yeah. And so you want to kind of think this as, this is a term, I don't care how complicated it looks, it's just a single term, minus another term. So you just change the conjugate, so you change the sign between two terms. So the minus is plus, but otherwise, it's like. And of course, I mean, if I multiply the numerator by that, I got to multiply the denominator as well by exactly the same thing, because that way we're multiplying by a form of 1, right? Which doesn't change the what the expression value is. Okay. So here we parentheses. And so when you multiply the conjugates, so of course when you multiply fractions, you multiply across, right? So you multiply the two numerators together. And since you're multiplying conjugates, what are you getting? It'll be the first term squared minus the second term squared. If you're not sure, just go with the FOIL, and it's messy and take longer. But so we're going to get the first term squared minus the second term squared. And then in the denominator, do yourself a favor and don't multiply anything out. Because what's going to happen is that you anticipated in these limit problems where you get 0 over 0, you expect a cancellation. So you don't want to like multiply out because you're going to have to end up factoring anyway if you want to cancel something. So just wait, right? Don't multiply out the denominator there. See if we can get some sort of cancellation. Okay. So what is the square root of x minus 2 quantity squared? Just getting rid of the square root. And then we have minus, and then 2 squared. And so you see the cancellation. It's kind of what we expect, right? Often it's just a cancellation like that. So when we cancel, what's left in the numerator? In the numerator?
Numerator, 0.
1, right? X minus 6 divided by x minus 6 is 1. And then you're right. I should have, in the denominator. So now we can try to evaluate the limit directly. And we get a nice finite number. So the limit is 1 over 4. Water. Oh, yeah, no. And it depends on, like, the grader, right? But I know that in many classes they would take off a point each time you do it. Because the limit, it's the weird thing, because the limit is the first thing you write, right? But it's actually the last thing that we did is evaluate the limit. We were doing lots of algebra, but technically you haven't taken the limit until the end, so you have to keep writing that limit statement until you get here where you actually found the limit. If that makes sense.
Yeah. And then for the actual response to the question, I think what the best information one is right. Limit x to 6.
Yeah.
Of x equals, and then in this case it would be 1 over 4.
Yeah.
Something like that.
So are you saying that the best one is you keep writing the limit until the end?
Yeah, I think at the end, Jenny's going to put 1 over, like, how we have it there,
Yeah.
right, like, limit.
Oh, like,
f of x
so
equals-
if you're going to box the answer, you want kind of like write down the original, right, problem. Because you're kind of summarizing the end result as a quarter, and that's what you box, is what you're saying?
Yeah, something like that.
That's good advice. I didn't know that, so. Anybody's actually watching these recordings, then good. That's good to tell them.
Myself.
Okay. All right. So what problem was that? 7, 8. So how are we doing time? Okay, good. So number 8. Oh yeah, so I do. We do want to actually be careful here. So be really careful. Don't write anything yet. I don't want to. Oops. There we go. So let's challenge yourselves a bit.
This looks like one of the questions we're gonna get on the quiz.
You know, there's a paranoia and worst case scenario thinking is a survival tool. Makes you the worst case scenario, right? You're ready.
Yeah, I'm already ready. So how did it? I'm like, I went class, I went to review. Still don't know how to do it.
At least they didn't ask us to solve climate change, right?
They got me trying to answer events.
Right. So did everybody get 0 over 0?
Yes.
All right. So that's an indeterminate form. So what do you want to try doing here in algebra?
We can back out the next movement.
That's right. Has it canceled anything? Well, no. So we have to do some more algebra. Yeah.
Well, it's not like it's listening, but like, we're listening, you're like, oh, they can? Okay. 'Cause
I
just
should have
like-
warned you, but I'm so used to like doing reviews. Let's see. Are you okay with that?
Oh, no, I was, it's because this morning I looked at one of the videos and then I listened to it for like 5 seconds and all of her teacher, and I was like, oh, they, it was just like a thought that I recommended. Okay.
Yeah, I think so. Yeah.
I was just curious.
We used to do hybrids where you had people in person and also online.
Mm-hmm.
All right. So, well, I mean, we do have a square root here, right? So we're gonna multiply by the conjugate. And so, of course, we're talking about the 1 minus the square root. This is the denominator. So what would be the conjugate of that expression?
1 plus
That's right.
square root of 5 minus 1.
That's right. Yeah, we simply changed the sign between these two terms. Yeah.
So we don't. Okay, I must have actually used this last time. You change what's in between. So even if that's a positive one, you don't switch to stable one. You need to change to what's in between.
That's true. I mean, right, it's like you have a cloud minus rectangle. The conjugate is cloud plus rectangle. Right? It doesn't matter like how complicated these guys are, right? Of course, you have to do the same thing with the top and bottom. So we're just multiplying by 1. Right. So when you multiply the conjugates in the denominator, what you guys get? I don't know. What is the final? Do you have the final answer? Okay. So what about just multiplying the denominators together here?
We got 1 plus 5 minus 6.
So, okay, let's be careful here. So we're going to have, let's do this on the side. So I guess this is a warning, I guess a good lesson here, right? Okay, so we know we're multiplying conjugates, so we get the first term squared minus the second term squared. Okay. So of course 1 squared is 1, and when we square the square root, we get rid of it. But be careful, right? It's minus this whole expression, so you have to use parentheses if you don't want to make a sign mistake. So it's minus, and then parentheses 5 minus x squared. So then you would have to distribute the negative into the parentheses. So you'd actually get x squared minus 4 if you slightly rearrange. So that's where I see students make mistakes. That's 1 minus this whole thing squared, but it's just sort of the square, but it's minus the whole thing, so it's minus everything inside. Okay. So okay. So can we do any other algebra here? And notice I didn't multiply the numerators out, right? Because we know at the end we're going to let x go to -2. So there's no reason to make it more complicated than necessary. We're going to get numbers. So we'll give you one more out. So we can do in the denominator. Yeah, x squared minus 2 squared is x minus 2 times x plus 2. Oh man, I hope I'm recording this. Yeah. All right. So now do we have that cancellation that we kind of anticipate in many of the problems? Sure, x plus 2 divided by x plus 2. So now we can evaluate directly, and you can tell me what we get. Oh, nice. So we get 1.
Did you say clarify that that's how I guess teachers want us to write it?
I don't know if you have the same professors, but it just listen to your professor. Like if your professor wants a kind of nice summary answer, kind of formal, yeah.
Mm-hmm.
I think she just wants it more like that as the exam. I don't know if she grades it or who grades it, but
Yeah, because typically students they'll slap the answer on the paper somewhere, and then they might claim that it's like that's not what they meant. But I don't know. So it's all clear to everybody that the answer is 1, and it's the answer to this problem. All right. So we had square roots in some of these problems where we then think about multiplying by conjugates to get rid of the square roots. So another issue you might come across is just fractions. Fraction-like expressions, right? You guys need a break or anything? So, for example, the limit they wrote as x goes to 10. We might get something like 1 over x minus 1 minus 1/9. Now that would be an easy problem, right? Because we would get 1/9 minus 1/9 is 0. So we don't want it to be easy. So we divide. That's it. So it's like the numerator has fractions, but that's within another fraction, right? So it's a fraction. It's fractionception, whatever. I don't think inception is a long, irrelevant reference, cultural reference, right? I don't know what you're asking. You guys know? Inception?
No.
Like a movie?
It's like a movie, yeah. It's exactly like a movie.
It is.
It is.
Oh, it's
Well, so it should be no surprise that you're going to get 0 over 0 when x goes to 10. On the top, you get 1/9 minus 1/9, which is indeed 0. The denominator, 10 squared minus 100 is 0. So that's an indeterminate form. Well, I mean, if you have fractions, really the quote-unquote natural thing to do is just to combine them, right? Okay. So we want to look at the numerator and combine the fractions. And so when you add or subtract fractions, what needs to happen? What do we need to find before we add or subtract fractions? Okay, right. And if you there's many common denominators, but there's always one that works if you're not sure, right? That's where you multiply the two denominators. So that's always a common denominator, if not the least common. Okay. So here our common denominator, or a common denominator, would be 9 times x minus 1. That's always a kind of fail-safe if you're not sure what the least common denominator is. At least you can multiply those to get a common denominator. Okay, so what do we need to do to introduce? So to introduce the common denominator in each term, you just have to multiply the top and bottom, right, by the missing factors. Okay. So for the first term, right, our common denominator is 9 times x minus 1, so we're missing a 9, a factor of 9, so multiply the top and bottom by 9. And for the second fraction, we're missing the x minus 1 factor, so multiply the top and bottom by x minus 1. Notice I'm just not thinking about the x squared minus 100 yet. Right? I'm just worried about cleaning up the fractions. All right. So okay. So now we have a common denominator. So we get 1 times 9 minus, and then 1 times x minus 1. And notice I'm using parentheses here. And then we divide by a common denominator now that we have it. All right, so we can distribute that negative. So we're going to get 9 minus x minus a negative 1 is plus 1. We have our common denominator. That's all still being divided by. So it looks like we get 10 minus x divided by 9 times x minus 1, all divided by, well, x squared minus 10, isn't that like x minus 10 times x plus 10? Yeah. Right, so there is a cancellation, but this is sort of tricky. So how do we, I mean, we have fractions within fractions, so how can we express this as a single fraction? So do you remember that dividing by a fraction is the same thing as doing what?
Divided by fractions
By the reciprocal, right? So of the denominator. So the fraction on top is going to get multiplied by the reciprocal of the bottom, so d over c. Okay. So the way I'm thinking of this is that we have the fraction on top, and then you're dividing by this fraction, so it's the same as multiplying by the reciprocal. So I think we're almost done. So now you can just think of that as having a 10 minus x on top, and then a bunch of factors on the bottom. Okay. So do you see cancellation?
Yeah, the x plus 10 and 10 minus x.
Let's see. So there's something, so you only cancel if two factors are exactly the same, right, on top and bottom.
Yeah.
So this is not exactly the same thing as that, that's for sure. Okay. In fact, this x minus 10 minus x doesn't look exactly like something in the denominator. But what you want to be on the lookout for, if you have a minus b and versus, like, say, b minus a, what's the relationship between these? And don't say conjugates because they're not. So you want to notice that, like, you can factor out a negative 1. Okay, and when you do, you're left with a minus b. Okay. You can check that works. It's negative 1 times a, then minus a negative b is plus b. So you're rearranging, you get b minus a. So you might want to be on the lookout for where the two factors are not exactly the same, but they're negatives of one another. And that way you kind of know that you're going to, well, just factor out a negative 10, say. So negative 1 on the top. And you'd be left with x minus 10 on top. So now you see that you could have an x minus 10 as a factor on top and bottom. So that means they're exactly the same. And then finally, you can take the limit. On top, we just have negative 1 left. On bottom, right, x goes to 10. So okay. Record this for posterity, and I'm doing a arithmetic on the side. Oh my god. Okay, times 2. So all right. Negative 1 over 1,000. So that's a rough one, but that's also on the homework. You have some fractions. Even worse, there's a problem where it's like fractions and exponents. So you might have to deal with that. Because we want at least talk about limits at infinity. Yeah. So limits at infinity, what does that mean? Let's see, try. Yeah. So limits at infinity, that has to deal with the long-term behavior of a function. So what we mean by that is we're going to let x go to infinity, right? So infinity is not a number, but it's just a way of saying that x gets arbitrarily large. And we want to know, in the long run, what does the function behave like for large x's? So we're going to write stuff like limit as x goes to infinity, because we're interested in how the following function behaves in the long run. And then we might get something like, let's say, it's fine. Let's keep it civil here. All right, something like that. Okay. So what's happening to the numerator as x gets arbitrarily large as it goes to infinity? What happens to the numerator? And to know what happens, you start thinking asymptotically, right? So you start thinking about the most powerful or dominating term. So what's the highest powered term in the numerator? The highest powered term would be the x squared term. It's the highest power of x. So is that what you meant?
Yeah.
Okay. Yeah. So this term is the highest powered term because you have x squared.
Oh, I just said the same one.
Yeah. It took me a second to register what you were saying. And what about the denominator? What's the highest powered term? Yeah. So this is just conceptually, right? We expect that for very large x's, the highest powered terms dominate. So our function, we anticipate, should behave like what you would get if you just consider the highest powered terms. Those highest powered terms dominate the other terms. And so if you simplify that, what would you get if you simplify this? Why? Right. So I can tell you that our limit is probably going to be 5, like for large x's. Now, so maybe from pre-calculus, you kind of remember that, like you look at the coefficient for the highest power term on top and bottom. But we're gonna be more rigorous here, right? And so instead, we're gonna employ this technique where we look for the highest power of x in the denominator. So that's x squared. I mean, it's not the only way, so I really don't know what maybe you guys know from class that you covered the way Esther introduced this. But let's say one of the standard ways is to denominator. Right. So the highest power of x in the denominator is x squared, and then what you're going to do is just divide both the top and the bottom by the highest power of x. So I'm going to multiply everything by x squared on top and bottom, right? So you're doing the same thing to the top and bottom. I mean, in terms of multiplication and division. So how does the how would we simplify the numerator? Right. What do we do in a situation like this where we have multiple terms on top, but a single term in the denominator there? Well, what we can do is just do the reverse of adding fractions, right? We have a common denominator, so we can just divide each of the terms, all of them, not just pick which one, all of them, by the x squared.
Does that go for both? Does that go for numerator and denominator?
Yeah, the same procedure is going to apply to both. All right. All right. And so now we can simplify. Of course, 10x squared over x squared is just 10. Are we okay with that? We have 2 over x, and then negative 7 over x squared. Is that okay, or should I provide more detail there? You're good? Okay. So, well, it's really weird. So over here, you understand that x squared divided by x squared is 1, right? Yeah. And then what about x divided by x squared? It's essentially properties of exponents. So this is what you were talking about. So without the fractions. But so what does that reduce to? Well, I mean, what does x squared really mean, by the way? It just means x times itself, right? And what's x divided by x? Yeah. Over x. Yeah. So that's why over here, right, we had 2x divided by x squared, so that reduced to just 2 over x. Yeah. Now, why did we do this? Why are we following this procedure of looking for the highest power term in the denominator and then just dividing the top and bottom by that highest power term? Well, it has to do with limits at infinity, right? Okay. What's the limit of a constant? Like if you have 10 or something. What's the limit of a constant? It's itself, right? Because if you have a constant, it's not changing with x. It doesn't even care what x does or doesn't do. It just remains itself. That's when the limit rules. It's just the constant. Whatever was there. Okay. Now, what if you have the limit as x goes to infinity of something like 1 over x? What is that equal to? Or if you'd like, if the 1 on top represents a tier, and x is like infinity. It's like what's I'm gonna mix my metaphors, right? One tear in an ocean, in a salty ocean, is nothing at all. Zero. So it's 0, right? If you look at the graph of y equals 1 over x, I'll just talk about the right-hand side. As x gets large, so x could be 10, and then 100. So x is just getting larger and larger. The denominator is getting larger and larger. But what's happening to the fraction then if the numerator is stuck at a certain number, but the denominator grows without bound? And the numbers are getting. It's not exponentially, but these numbers are getting smaller. They're approaching what? So as x goes to infinity, the graph is approaching the x-axis, so the y values are approaching 0. Right? So what we want to know is that if you have a limit at infinity, and you have something like a constant divided by x or x squared or any positive power of x, this is always going to be 0. Because the numerator is stuck at a number, but the denominator grows as large as needed to get as close to 0 as you want to the whole fraction. So that's the motivation, right? That's the reason we want to divide by the highest power of x for limits at infinity. Because we only have, now we just have constants. So the limit of a constant is the constant. And what's the limit of 2 over x as x goes to infinity?
0.
Yeah. And what's the limit of 7 over x squared as x goes to infinity? The numerator is stuck at 7. The denominator grows as large. So what's 7 divided by quadrillion close to? Yeah. Okay, in the denominator, this is a constant. So what's the limit of the constant? Yeah. And what's the limit of 3 over x as x goes to infinity? And 1 over x squared as x goes to infinity? Right. So you see that by dividing by the highest power of x, we either ended up with constants or a constant divided by some power of x. So now it's easy to evaluate the limit as x goes to infinity. And so we're just left with 10 divided by 2. So the answer is 5. Just kind of like what you would get if you see the pre-calculus concepts as well. All right. This was example number 10. Do another one quickly, just because, or 2 quick things to show some stuff. All right. So how about like x squared plus 5x minus 1 divided by x cubed plus whatever 7x plus 3. Yeah. So this is a limit at infinity because x is going to infinity. And for that kind of limit, L'Hopital's rule, we want to look for the highest power of x, right, in the denominator. So what's that highest power of x? X cubed. So now we're going to divide the top and bottom by that highest power of x. It actually also works if you choose the highest power of x in the numerator. But yeah, I mean, so I'll just do professor because it doesn't matter. You just kind of so some professors say look for the highest power of x in the denominator specifically, just to give you a guideline. Other professors just say look for the highest power of x anywhere, and that's what you apply. Figure out. So let's simplify. When you're dividing the three terms on top by x cubed on bottom, what do you get?
X squared over X cubed.
Okay.
One over X cubed.
And on bottom, you're likewise dividing all the terms on top by x cubed. So now we do the simplification here using our algebra skills, right? Properties of exponents. Yeah, but you know, yeah. Okay. And now we can easily find the limit, okay, as x goes to infinity. So let's go term by term. The 1 over x as x goes to infinity goes where? Yeah, finite number divided by something that was arbitrarily large.
Is it the same thing for X squared? 0?
That's right.
Okay.
And
0.
right, and the bottom,
1.
it's a constant, remains itself.
0. 0.
So at the end of the day, what do you get?
0.
Which is equal to? That's right. So 0 divided by non-zero is 0, and that's a perfectly legit number. So that's our limit. Okay. Now, lastly, right, and notice that if you recall some pre-calculus, that's what they would have taught you, that if the exponent, if the degree of the polynomial on bottom is bigger than the degree of the polynomial on top, you'd get a 0 for a horizontal asymptote. And it's also possible the limit doesn't exist. So if the exponent, hey.
I'm so sorry. I just need to grab a paper real quick from paper.
A piece of paper?
Well, it was from my. I'm so sorry.
Oh, that's fine. That's cool. I didn't see anything.
Okay, it's okay.
I didn't touch anything.
Yeah,
All right.
Sorry about that. I'm so sorry.
Good luck, man. Poor guy. I probably had no my preparing material, right? Right. So you do the same thing here. It's a limit at infinity, but this time, let's just cut to the chase. I would divide everything by x cubed on top and bottom. So after we simplify and then we take the limit as x goes to infinity, we have our constant, and the rest of the terms go to 0. Wait a minute. Yeah, it's fine. So what do we get? 1 over 0. So what does that mean? Does not exist. And it may be later on you'll talk about limits that are infinite, but I think for this homework it says does not exist or find a thing. Yeah. All right. Well, that covers most of it. We didn't get to continuity, so maybe if you have questions on that next time.
Well, are you doing like the homework? Like, see?
This is for the homework 4 I was going to going over that it's due Tuesday, I believe.
Do you know if there's continuity?
The homework? Yeah.
Oh, okay.
I'm looking at it.
Cause I was like,
Well, I forgot this week.